All right, we're going to start our unit on vectors. All right. So it says, looking at some vectors that we're going to be talking about, it says it's been a dynamic lecture, but now that it's over, it's obvious that my professor is exhausted. She's slouching motionless against the board. And what's that? The forces acting against her body, including the pull of gravity, are appearing as arrows. I know that mathematics reveals the hidden patterns of the universe, but this is ridiculous. Does the arrangement of the arrows on the right have anything to do with the fact that my wiped out professor is not sliding down the wall? In other words, what's keeping her from falling down? There's all kinds of forces acting against her body to keep her in that position and not sliding down onto the floor. Okay, it says ours is a world of pushes and pulls. For example, suppose you're pulling a cart up a 30-degree incline, requiring an effort of 100 pounds. This quantity is described by giving its magnitude, which is a number that's indicating size, including a unit of measure, and also its direction. Its magnitude is 100 pounds, and its direction is 30 degrees from the horizontal. Quantities that involve both a magnitude and a direction are called vector quantities, or vectors for short. Here's another example of a vector. It says you're driving due north at 50 miles an hour. Okay, your direction would be due north, and your magnitude would be your speed, which would be 50 miles an hour. If you look at this sign, it says the sign shows a distance and direction for each city. Because it has a distance and a direction, we can consider each one of those a vector, because it's giving you a distance and it's telling you the direction to go. Some quantities can be completely described by giving only their magnitudes. For example, the temperature of the lecture room that you just left is 75 degrees. This temperature has magnitude, 75 degrees, but no direction. Quantities that involve magnitude but no direction are called scalar quantities, or scalars for short. Thus, a scalar has only a numerical value. Another example of a scalar is your professor's height, which you estimate to be about 5.5 feet. Alright, so what is it with all this stuff? Alright, let's talk about a directed line segment. A line segment to which a direction has been assigned is called a directed line segment. Notice it's not just 2 points. See how there's an arrow? So it's also giving me direction. That's why we don't call it just a regular line segment. It's a directed line segment. And this figure shows the directed line segment from P to Q. We call P the initial point, and we call Q the terminal point. And we denote this directed line segment by what you guys used to call that ray over PQ. Alright, the magnitude, which is the length of the directed line segment, is its length. We denote this by these double bars PQ. And you'll also see it just in regular bars. It'll look just like absolute value bars. Some textbooks use the double lines, some textbooks only use the single lines. It's really just the absolute value because it's the distance. I mean, if you're finding the length, you're going to be using the distance formula. And because distance is non-negative, we don't have negative magnitudes. Geometrically, a vector is a directed line segment. So when you have a directed line segment, really what you have is a vector because it has length and direction. Vectors are often denoted by bold-faced letters such as V. It says if a vector V has the same magnitude and the same direction as the directed line segment PQ, we write the vector equals PQ over the ray. So if you look at this ordered pair, A, comma, B, and you connect it to the origin, and you connect it by putting an arrow, not after it, but before it. They don't put that dot, but they really should. Okay? That length, including its direction, would be the vector A, comma, B. Okay? Alright, so figure 6.49 down here shows 4 possible relationships between vectors V and W. In A, the vectors have the same magnitude, they're the same length, and the same direction. So we would call these equal vectors. For B, vectors V and W have the same magnitude. In other words, they're the same length, but they're different directions. V is heading this way, W is slightly lower. Okay, V and W and C have the same magnitude. In other words, they have the same length, but they have opposite directions. And then for D, they can have the same direction, but have different magnitudes. In other words, be different lengths. All right, a two-dimensional vector. A two-dimensional vector V is an ordered pair of real numbers denoted in component form as AB. And component form means you put these, I don't know, what do you call them, pointy parentheses instead of regular parentheses. Okay? The numbers A and B are the components of vector V. The standard representation of vector AB is the arrow from the origin to the point AB. The magnitude of V is its length of the arrow, and the direction of V is the direction in which the arrow is pointing. The vector 0, 0, 0, called the zero vector, has zero length and no direction. Alright, so how in the world do you figure out these A, B coordinates? Well, if you're at the origin, it's easy. It's whatever A and B are. If you're not, then we have what we call a head minus tail rule. And it says, if an arrow has initial point x1, y1 and terminal point x2, y2, it represents the vector. So basically, it represents the vector AB, but to get A, you subtract the x coordinates, and to get B, you subtract the y coordinates. The magnitude, in other words, how do you figure out the length? Well, the magnitude or length of vector V is also called the absolute value of V. So it's usually denoted by bar V. Again, you might see that double line in some textbooks. Note that it is a non-negative real number. It's not a vector. The magnitude itself isn't a vector. It's just the length of the vector. And again, we're finding the distance, so it's nothing more than the distance formula. Okay, what's easier is to figure out what your A and your B are first, and then to get the distance, you just take the square root of A squared plus B squared. Alright? So, look at this example. It says, find the component form and magnitude of the vector V represented by RS. See, we're not at the origin. Normally, if we were at the origin, you would just take your terminal point, and that would be your A and that would be your B. But we got to figure out our A and our B of this vector, because we have an initial point and a terminal point. So this would be x1, y1. This would be x2, y2. So if I have to figure out the vector, I would take x1, negative 1, minus x2, negative 4. And to figure out B, I would take 6 minus 2. That turns positive, which gives me 3, 4. And 6 minus 2 gives me 3, and 6 minus 2 is 4. So this vector would be represented by 3, 4. To figure out its length, how long it is, okay, we use the distance formula. Now normally, again, we would have to do negative 1 minus, but we already did that. We already figured out what A and B are. So instead of writing all this out, since we already figured out what it was, alright, then all I have to do is take my A squared plus my B squared, and that gives me 9 plus 16 is square root of 25, which is 5. This has a length of 5 units. Okay? Alright, so this one says, find the component form and magnitude of vector V represented by PQ. Okay, PQ is here. Alright, and it says P is at negative 3, 4, and Q is at negative 5, 2. So, to figure out the component form, the vector for PQ would be x2 minus x1, comma, y2 minus y1. That turns positive and gives me the vector negative 2, negative 2. And if you look, what you're doing basically is, when you're finding the vector, you're saying if I moved this to start at the origin, just like I did here, where would this end up if I shifted it down to the origin? Well, it would end up at 2, negative 2. Okay? And then to find the magnitude, To find the magnitude of v, you take the square root of a squared plus b squared. So that's going to be the square root of 4 plus 4 is 8, which is going to be 2 square roots of 2. So there's my component form, and there's my magnitude. Okay. Alright, you try this one, hit pause, come back when you're ready. And hopefully you got 3. Alright, so if we want the vector from PQ, we're going to take x2 minus x1 and y2 minus y1. Sorry, don't make them round. Double negative turns positive, that's going to be -1, -5. To find the magnitude of v, square root of a squared plus b squared gives me 1 plus 25, which is the square root of 26. Alright, this one says, show that the arrow from R to S is equivalent to the arrow from P to Q. Well, we can use the H and T rule, head minus tail rule, or we can use magnitude, either way. If I use the head minus tail rule to do vector RS, I would do x2 minus x1, y2 minus y1, which gives me double negative 3, 4. And if I do vector PQ, I get 5 minus 2, 3 minus a -1, which gives me 3, 4. If I positioned both of these at the origin, 2, 3, 1, 2, 3, 4, they would both be right here. Okay, and that shows that they are equal. They have the same direction and the same length. Well, this shows me they have the same direction. The magnitude will show me they have the same length. If I do the the magnitude of vector RS, I would have the square root of 3 squared plus 4 squared, which would be the square root of 45. Yeah, which would give me 3 square roots of 5. And then if I did the magnitude of vector PQ, I'd have the square root of 3 squared plus 4 squared, which is the square root of 45. It'd be 9 plus 16 is 25, 25. They have the same length also. Okay? Alright, so let's do this again. Alright, they want us to do u and v. If I do vector u, that's this one. So we would have x2 minus x1, y2 minus y1. That's going to give me 3, 6. And if I do v, that's going to be 3 minus 0, 6 minus 0, which is 3, 6. That shows that they're equal. I can also show that their magnitudes are equal. To do the magnitude of u, it's going to be the square root of 3 squared plus 6 squared. There's my 45, which is 3 square roots of 5. And if I do the magnitude of v, I get the square root of 3 squared plus 6 squared equals the square root of 45, 3 square roots of 5. So they have the same direction and the same length. They are equal. Alright, you try one, hit pause, come back when you're ready. And hopefully you got yes. Alright. It says let u be the vector represented by RS. So u is going to be 9 minus 3 and 13 minus 4, which is going to be 6, 9. And if I do v, that's going to be, v is to represent OP. So that's going to be 6 minus 0, comma 9 minus 0, which is at 6, 9. So yes, they are the same. Okay, try another one. Hit pause. Come back when you're ready. And you should have gotten no. If I do RS, and they're calling that one U, it would be 15 minus 7, negative 9 minus a negative 3, which would be 8, comma, negative 6, double negative. V is going to be 8 minus 0, negative 12 minus 0, which is going to be 8, negative 12. They do not match, so no, they are not the same. Alright, adding, subtracting, and multiplying vectors. I'm going to show you geometrically how to add and subtract vectors. You don't have to do it geometrically. Algebraically it's really easy, but it's kind of helpful if you can see how these are added. It says in the tail to head representation, the standard representation of U points from the origin to U1, U2. So they're talking about this point right here. The arrow from U1, U2 to U1 plus V1, U2 plus V2 represents V. Okay, so then they added a vector V. And if you basically then draw your, this is the way that makes most sense to me. So you go your first vector, and then you add your second vector, and the sum is right here wherever they end up. That would be your resulting vector, that ordered pair. Or you can do it using a parallelogram representation where you basically put U in standard position, put V in standard position, and then if you basically drew a line in the middle, and then wherever they met, that would be again the sum. When you multiply k times a vector, k is called a scalar, and it's just basically a numerical constant that is going to, that you multiply, that either makes your vector longer or shorter. So if here's U, they doubled it here for the middle one. They took half of it here, and here they doubled it but turned it around and changed its direction. Okay. Alright, so vector addition and scalar multiplication. Algebraically, it's very simple. If you have a vector U that has coordinates U1, U2 and vector V, V1, V2, if you want to add them, you basically add their first coordinates and add their second coordinates for your new first and second coordinates. Subtraction, same way. Just watch your subtraction and signs. If you're going to multiply, they call it scalar multiplication. You take your vector times some numerical scalar. You just multiply everything inside. It's kind of like the distributive property. Alright, so it says let U be negative 1, 3 and V be 4, 7. Find the component form of the following vectors. They want U plus V. Well, U is negative 1, 3 plus V is 4, 7. So my resulting vector, U plus V, is going to be negative 1 plus 4, comma, and then your Y's, 3 plus 7, which is going to give me 3, comma, 10. Yeah? And watch. I was going to try and draw it, but I remembered I did this. Okay, here's U, negative 1, 3. So that would be from here to here, yes? Now, this says V. So for V, you're supposed to go 4 over. From here, I'm going to go 4 over and 7 right. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7 puts me right there. And so that's where I would draw V to. And then in red here, there's the sum. And if I get the coordinates of that point, that is at 3, comma, 10. Yeah? Pretty cool? Alright, this one they want me to find 3U. So they want me to take 3 times negative 1, 3, distribute, and that gives me negative 3, comma, 9. Okay. If you want to draw it, a little more complicated, Alright, this would be, they want 3 negative 1 3s. So negative 1 3, there would be 1. There's your u. Negative 1 3, there would be 2 u's. Negative 1 3, there would be 3 u's. And this puts you at negative 3 9. Alright, subtraction and multiplication here. So they want us to figure out what 2u is. So that's going to be 2 times negative 1 3, which is negative 2 6. Then they want you to figure out what negative 1v is. That's negative 1 times v, which is negative 4, negative 7. Then they want me to add those. So if I take negative 2 6 plus negative 4, negative 7, I'm going to get negative 2 plus a negative 4, 6 plus a negative 7 gives me negative 6, negative 1. Yeah. Alright, you try one, hit pause, come back when you're ready. And, oops. Sorry. And hopefully you got 1. Come on. Alright. So they want us to find u minus v. So I got negative 1, 1 minus 5, negative 7. Distribute that negative. I get negative 1, 1 plus a negative 5, positive 7. So I would get then negative 1 plus a negative 5 and 1 plus 7. That gives me negative 6, 8. Okay, try this one. Hit pause. Come back when you're ready. And you should get 56, 72, negative 72. If I multiply negative 8 times u, that's negative 8 times negative 7, 9. Distribute, that's 56, comma, negative 72. Alright, try this one. Hit pause. Come back when you're ready. And hopefully you got 2. Alright, it says find the component form and magnitude of the vectors PQ plus 2RS. Well, I got to figure out what those vectors are first. Alright, so to figure out vector PQ, it's going to be negative 1 minus a negative 5, negative 7 minus a negative 2, double negatives, and I get 4, comma, negative 5. If I find vector RS, that is going to be negative 13 minus a negative 9 and 4 minus a negative 1. Yeah, double negatives, so that's going to give me negative 4, comma 5. Yeah. And then they want me to do v plus 2u, or pq plus 2rs. So pq plus 2rs is going to be 4, negative 5 plus 2 times negative 4, 5. That's going to give me 4, negative 5 plus negative 8, 10. And that's going to give me 4 plus a negative 8 is negative 4. Negative 5 plus 10 is 5. So there's my component form. The magnitude of that is going to be the square root of its a squared plus b squared, which is 16 plus 25, which is the square root of 41. Alright, so how do you find the magnitude of a vector? The magnitude of a vector is the square root of a squared plus b squared. 5. How do you use a directed line segment arrow to represent a vector? You put a point on the terminal, or initial I should say. Initial. You put the other point at the terminal. And you put an arrow on the end. How do you add, subtract, and multiply vectors? For add and subtract, you add and subtract coordinates. For scalar multiplication, you multiply the coordinates by the scalar. Alright, so we are at homework. Oh, no, one more. How do you find the components of a vector? Head minus tail rule. So for vector v, you do x2 minus x1 and y2 minus y1. Alright, so we are at homework. Happy homeworking, and I will see you next time.